Hello everyone. Today we are going to present the paper called Demystifying NCCL. So, what is NCCL? NCCL is the high performance GPU communication library. It is for multi GPU and multi node training. It provides optimized collective operations like all reduce, all gather, etc. Now, let us look at the motivation behind NCCL or nickel. Look at this training iteration time breakdown of many real world training tasks. As the number of GPUs increases, the communication overhead also increases. It creates a communication bottleneck. Many papers have pointed out that this happens because the network bandwidth isn't efficiently utilized. Hence, many GPU communication libraries emerged, and NCCL became the de facto standard. Both PyTorch and TensorFlow rely on nickel. NVIDIA has made nickel open source, but still it's not well documented, and developers treat it as a black box without understanding the internal workings. Here in this paper, the authors have tried to demystify NCCL by explaining the protocols and algorithms used inside. Let us look at the basic API and execution flow for nickel. Every nickel operation starts by creating a communicator, just like MPI, which defines the group of GPUs involved. It has peer to peer and collective operations. We can wrap these sequential operations in NCCL group start, nickel group start, and nickel group end calls. They basically package multiple operations into a single launch. This reduces overhead. Finally, the communicator has to be destroyed to free resources. Now, let's talk about communication channels. Nickel divides communication work into multiple channels. Each channel handles a slice of data. Each channel is mapped to a CUDA streaming multiprocessor. Think of it as CPUs have many cores inside them. Similarly, GPUs have many streaming multiprocessors inside. Having these communication channels achieves higher bandwidth and better parallelism. Here we can see ring and tree topologies. Nickel automatically detects the GPU interconnect like NVLink or PCIe. It then builds the optimal logical topology. It may use a ring or tree or a combination of rings. The user does not have to manually configure this. Now let's look at protocols. What is the protocol? Protocol is basically how data is moved inside the algorithm. This decides the low level data transfer method, which is optimized according to message size. Now nickel has these three protocols: simple, low latency, and LL128. Simple protocol has high bandwidth. It uses memory fences to achieve synchronization, and the payloads are large tensors. It is basically good for large tensors. But the latency is highest for the simple protocol, but it achieves the highest bandwidth. For low latency protocol, it is low latency. It is good for small messages. It uses flags for synchronization instead of high overhead memory fences. So it is good for small message sizes, but the bandwidth is not good. And here at LL128, it is improved low latency protocol. It uses it is balanced between simple and low latency. Basically, it the payload is bigger than low latency. It also uses the same flag based synchronization, but the payload is bigger, which helps with the bandwidth. Now let's look at intranode communication. So intranode communication inside NCCL, inside nickel. Here, see the scenario where GPU 0 and GPU 1 are inside the same node, and GPU 0 has to transfer data to GPU 1. So they can either use the host memory, which is shared, and from the send buffer of the GPU 0, it goes to host memory and then to the GPU 1. This is the normal path, you could say. Now let us look, we can completely bypass this host memory, and we can directly go through the PCIe bus or NVLink. if it is available, NVLink is preferred. But here first it goes into a intermediate FIFO buffer inside GPU1, and we can also avoid this completely if we use P2P direct mode. If P2P direct mode is enabled, then data will directly go from GPU memory in GPU0 to GPU1's receive buffer, which can happen through NVLink or PCIe bus. Note that both GPU0 and 1 must belong to the same process. Now let's look at inter-node communication. Here GPU0 is inside node 0 and GPU1 is inside node 1. GPU0 wants to send data to GPU1. So let's see how we can achieve that. So we can use the host memory as a staging area. So basically data will be sent to host memory first, and then the NIC will send it to the host memory of node 1, and then from there it goes to the GPU memory. Now this can happen through RDMA as we have seen in class, or the normal TCP sockets. But the problem is we are first writing to the host memory and we don't want that. So we can totally bypass this host memory if GDRDMA, GPU direct RDMA optimization is available. We can directly, the NIC will take the data from the GPU's memory and it will write it directly to the receive buffer, to the receiving GPU's memory. Note that there will be some intermediate FIFO buffers involved, but it will be much faster anyway than writing to the host memory. And by the way, in these like internode communication, there's a proxy thread of the CPU which basically does all the network operations for the GPU. Now let's look at collective operations and primitives. Collective algorithms and primitives. Nickel provides several collectives like all reduce, all gather, reduce scatter, etc. Each collective can be implemented by several algorithm protocol pairs. Nickel runtime selects the most efficient algorithm protocol pair based on message size, interconnect technology, number of GPUs, etc. Algorithm determines the logical topology that Nickel uses to move data between GPUs, and protocol is the simple LL128 that we were talking about, which determines the low level data transfer method. Algorithm is about the logical topology like ring, tree, etc. Now let's talk about iterative execution and communication primitives. So in Nickel, large tensors are split across many channels, and each of them is given to a SM, right? Nickel dynamically chooses the number of channels based on factors like tensor size, GPU type, topology. Total count is the total number of elements participating in the collective. Channel count is total count divided by number of channels. Within each channel, data is transferred in small chunks. This is the channel count, and within each channel data is transferred in small chunks. And there is a loop count also, which is basically the channel count divided by chunk size, and it tells NCCL, it tells Nickel how many times a channel must run its inner pipeline to, because like the smallest operation that can happen at once is the chunk count. Now let's see this table, which where we see all the steps in one loop iteration of Nickel ring all reduce. Here for step 0, send, and then receive reduce send, receive reduce copy send, receive copy send, receive. So let me explain this. So in a ring all reduce, first we have 4 arrays in 4 different GPUs. So the first thing will be send. First operation will be send, because there is nothing to reduce in the first step. In the first step, there is nothing to reduce, so each GPU will have to send the data to its corresponding GPU. After the first step, each GPU will be receiving something and it will also be sending something. So now the reductions will begin, and they will go on till from the first step 1. Here it was step 0. From step 1 to step k minus 1, k minus 2, the same operation will happen, receive, reduce, send. At step k minus 1, now we have receive, reduce, copy, send. This is the point where the reduce scatter happens, and now the data is ready, the element is ready, and it has to be copied to the destination buffer basically. So that's why we have to copy it. Now after these four are about the all gather completing. So now all the deductions are over. So receive, copy, send is the only operation left. So basically each GPU has to receive something and it will send something, and it will also copy to the destination buffer. Finally, in the last iteration, each GPU only has to receive and nothing to send. So that is how ring all reduce algorithm is implemented in NCCL. Thank you.